Okay, we're gonna get started. We're gonna finish up the last part here, 17 officially. And then for the rest of the day, we'll just do a little bit of reviewing. Then we'll call it a day at some point. So we got to 17 here, which is equilibrium, and we started talking about equilibrium. And again, a reminder that equilibrium does involve a special type of reaction, which is a reversible reaction. And as we talked about, it will have these arrows that head in both directions. And again, there is a forward direction going from reactants to products, and a reverse direction as the products sort of recombine and make our reactants, which is referred to as the reverse direction. So again, typically what happens in this situation is if you start with just reactants, you will pretty much have just the forward direction happening as you have the availability of really only the reactants there to react with one another. So that would kick off the forward direction of this reaction. At some point, you will start to increase the amount of products. You'll actually start obviously to decrease the amount of reactants. And at some point, you will create enough products that they will basically start to combine with each other and actually start heading in the opposite direction. And this will kind of continue until chemical equilibrium has been reached. And as we talked about, I think last time as well, chemical equilibrium or reaching equilibrium doesn't necessarily mean that you have the same amount of everybody on both sides of the arrow. What it is really referring to is the rate of these reactions. And again, the rate of the forward reaction will then equal the rate of the reverse sort of reaction. And essentially, what that does is, as I mentioned, pretty much will lock everybody into place in terms of their concentrations or pressures if we're talking about gases. And they'll be able to really maintain those concentrations or pressures as long as you don't do anything to kind of screw it up. And it'll kind of go back and forth at the same rate. So again, wherever they sort of lock into in terms of when equilibrium is reached, they will maintain that. Now, when we look at something that has reached equilibrium, sometimes it does appear that perhaps the reaction is over. So you may be looking at a beaker and it may just kind of come to rest, and it may just look, orange or yellow or whatever it may be. Kind of like that experiment we did at the very end there. When we changed colors, say maybe it went darker red or yellowish or something of that nature, and it may look like those reactions are pretty much done. But there is a lot of activity that's happening to maintain that. So although when you may look at your beaker and this reaction has reached equilibrium, and maybe it just looks kind of reddish or whatever it may be, and it may look like nothing else is happening, there is a lot of activity of reactants going to products, products going to reactants, again, just happening at the same rate to sort of maintain what you're looking at. And that is something to keep in mind that, if you super zoom in, there's a lot of activity sort of happening. So picking up sort of where we left off, as I mentioned before, it is a dynamic process where basically the reactants and the products do remain constant. And again, once that situation of equilibrium has been reached, they pretty much can maintain that sort of indefinitely. Again, as long as nothing sort of happens to mess up the equilibrium. So as I said, it is static sort of on the big level. Like if you looked at your beaker, it doesn't look like very much is happening, but there is a lot of activity happening sort of below the surface, if you will, on the molecular level to maintain that system at equilibrium. So although you may not be able to visually sort of see things happening, there's a lot of activity sort of happening as the forward reaction and reverse reaction are continuously happening. And as we can see here, we could have our system at equilibrium, and we got our kind of amounts of each of these guys at the beginning here, really just reactants. We use up a little bit of reactants to make some products. We continue to use up reactants to make more products. And then eventually everybody will sort of maintain their concentrations as it reaches equilibrium. So again, we do see at the very beginning, in this case, since we have all reactants, the forward reaction is predominating. Around here, we're starting to get some of the reverse reaction sort of happening. And again, we're going to get to that rate of the forward is going to equal the rate of the reverse at the very end, where everybody's be able to maintain their concentrations. And if you look at it graphically, when you look at a graph of your, say, your reactants versus your products over time, this is typically what you will see at the very beginning. For example, again, we have kind of the forward reaction happening, and that means our reactants are going to become products. So we'll start to see really our reactants being converted into products, and our products will start to increase. At some point, the lines will basically level out and plateau out. That is the point where equilibrium basically has been reached. It doesn't necessarily mean that, all your reactants and products need to hit exactly the same spot. You could have something like this, and that would be, for example, where it sort of levels out, would be where equilibrium would be reached in that particular case. So if you look at it graphically, it is the point where basically all the concentrations, for example, pretty much sort of flatten out and level out, if you're looking at concentrations. So chemical equilibrium, when we do reach that, the rate of the forward reaction does equal that reverse reaction as we talked about. So for example, if we look at this reaction here, that is, say, at equilibrium, and we decide to add more H2O to this, what's going to happen to sort of the concentrations of everybody in this case? Well, at this point, we have a situation where everybody is going sort of forward and reverse here at the same rate. And now we're going to basically add more of our water in this case. That's going to increase, obviously, at the beginning part here, the amount of water that we're adding. And ultimately, what that's going to do is, because there's now more water available, water and CO really shouldn't have too much trouble finding each other. And that's going to kick off actually the forward direction in this case, right? Just the availability of all reactants. There's a greater availability of reactants there, and that's going to allow them to combine. And that should kick off really that forward direction occurring. That means that when we look at something like H2, we would expect the concentration of it to start to increase in this case, right? Because we're kind of kicking off the forward reaction. So we would expect this guy to increase. We would also expect the CO2 to increase as well. Now, when we look at the CO in this case, the concentration of that should actually come down because we're doing the forward reaction. And the only way to make products is we need both reactants to react with one another. So we should actually see a decrease in the amount of CO in this particular case. Now, water is sort of an interesting one in a sense, because what we would actually see with water is we would actually see it increase because we added it. But once it starts reacting with the CO, we should then see water start to come back down because we'll need it to make our products and stuff like that. So in the case of water, you may actually end up greater than where you started with, and you only are going to end up greater when you started with because you just added it yourself to it and you sort of artificially increased it. But you then should start to see it come back down as it reacts with the CO, and that forward reaction pretty much predominates there. Any questions on that there? Now, if we look at something, maybe. We look at the same reaction, I add H2, take a moment and think about how everybody's concentration should change in this particular case. Okay, so looking at this, in this case, we're going to be increasing our H2 in this case. That is, much like in the previous example, going to actually make the availability of our products more available than, say, our reactants. So what that's going to do is going to allow them to come together a lot easier, and that actually would kick off the reverse reaction to occur in this case, again, because of the greater availability of our products. That is going to mean kind of like in the last case here, because the reaction is heading towards our reactant side in this case, we should see an increase in the amount of water in this case. We also should see an increase in the amount of CO in this case. The CO2 should come down because, again, it is needed to make the reactants as the reaction is heading from products to reactants. And the case of the H2, a similar sort of thing is going to happen. We will see it sort of artificially rise because we added it. But once it starts reacting with the CO2, it should really start to come back down. And again, you may end up, as I mentioned before, a little bit higher than you started with because you artificially added it. Any questions on that there? So there is a relationship that happens in these type of reactions, which is known as the equilibrium constant, and that is what capital K stands for. And it is a capital K, that is the equilibrium constant. Not to be confused with lowercase k, which is the rate constant, has to do with rate. So it's definitely capital K here. And there is a relationship that if you take basically your products, the concentration of your products, divided by the concentration of your reactants, it will give you this constant value. And when we see these brackets, it does mean concentration. And it does mean typically molarity is usually what we're talking about in this particular case. So you could write the equilibrium constant for a reaction by taking the products over the reactants. In this case, the coefficients become the exponents when you do so. So those coefficients become the exponents. And this type of K is what is sometimes referred to as the Kc value. And it's a Kc value because we're using concentrations. You could also do this if there were gases, for example, and all these guys were gases. You can write an equilibrium constant using pressures, where you take the partial pressure of C to the C, partial pressure of D to the D, partial pressure of A to the A, and partial pressure of B to the B. And this is sometimes referred to as a Kp value. And this would be if we had gases and we had pressures instead of concentrations. There are all kinds of K sort of values. There's Kc, Kp, Kw, which we used before. It's also an equilibrium constant. Ksp, Kf, Ka, Kb, also known as basically Chem 1b. If you take that class, you talk about all the different types of equilibrium constants that they are. But they are all essentially the same. You take your products over your reactants. There are a couple of things that do not sort of affect equilibrium, and there are a couple of things that we do not include in the K value. So what is not included is anything that is a solid or a pure liquid. So anything that is basically a solid or a liquid is not included in the equilibrium constant expression. You just leave it out. That pretty much leaves only two things that are included. And the things that are included are things that are aqueous and things that are gases. So anything that's an aqueous thing, a solution, and anything that's a gas basically is included. As we might talk about a little bit here, solids are really not included because frankly, it's kind of like a rock into like a beaker, right? It's just kind of going to sit there. Can't really do much other than, until it dissolves or something like that. So it's not going to affect anything. And the concentration of pure liquids are pretty much constant throughout the entire process, like water. So that doesn't change very much. So solids, liquids, we leave out. Anything that's aqueous or gas is included. And we also do our coefficients as the exponents. Now, the equilibrium constant is a constant value at a constant temperature, or at a temperature, I guess is a way to put that. So the only thing that could affect the value of the equilibrium constant is temperature. So if you change the temperature, you will have a different equilibrium constant for that particular reaction. So if you do not change the temperature, you will have the same value of K for that reaction no matter what you do. Um, so when we talk about temperature and different values of K, what that means is if I were to take an equation and I calculated K at 25 degrees Celsius, let's just say it was 10, for example, and I calculated K at, say, 50 degrees Celsius, and we'll just say it was, I don't know, 40. Right. At 25 degrees Celsius, I pretty much could do this reaction any way I want, which I mean is I could start with all reactants. I could start with all products. I could start with a little bit of reactants and some products. I could start with a little bit of everybody. And this reaction will always come to rest in terms of their products over reactants with the same ratio of numbers, basically, and will give you the same value at 25 degrees. In my example, I could do 6 different experiments where I use different amounts of reactants, products, reactants, put it all together. And if I calculated the equilibrium constant for those 6 reactions or experiments at 25 degrees, as long as it's say 25 degrees, I should always hit in my example 10 basically as my equilibrium constant. Now, if I take that same reaction, I take the same starting amounts and those type of things and those same 6 experiments, but the only thing that I change is I move it up to 50 degrees. I should hit for all 6 experiments 40 as my equilibrium constant. The difference in temperature is the comparison between what the equilibrium constant is at 25 degrees and what it is at 40 degrees. Those values will be different. But once you keep the temperature at a certain level, you can do the reaction as many times as you want and you'll get the same value. Any questions on that? Now, that is also something that's very hard for a lot of people to sort of understand. They figure, well, if I did 2 experiments and I started with a lot more reactants than I did the first time, and then I did the second time, shouldn't I end up with sort of this different sort of number? And you won't. You could, again, start, like I said, with different amounts of reactants, different amounts of products, all reactants. It will always come the same. So the very simple way to sort of figure that out is, let's just say we wanted our equilibrium constant to be 2, right? And there's many different ways that you could get to in terms of ratios, right? You could take 8/4, right, equals 2. You could take 4/2 equals 2. You could take 2/1 equals 2. So all those are sort of different numbers, right? But they all come out to the same number at the end when you divide it. And that's sort of what happens in the equilibrium process here. Even though you're starting with different amounts, that ratio of products to reactants, when it reaches equilibrium, will always be basically the same number as long as the temperature remains the same as you're comparing each of those reactions. Any questions on that there? So here again is an example of writing one, and this is what would be a Kc type of equilibrium constant. We would take the concentration of NH3, we would square it because of the coefficient that is there. So that is where that comes from. We would do the same thing. We'll divide it by our reactants. And once again, that 3 is here. Nothing is written here, so it's assumed to be 1 like normal in chemistry in this case. This is also, as you can see here, gases. So as I mentioned before, you could write a Kp expression for this, which would be the same thing as the partial pressure squared of NH3 divided by the partial pressure of N2, partial pressure cubed of H2. And again, here you would use pressures. Now, if you actually wanted a number for any of these things, you would need equilibrium concentrations or equilibrium pressures to go into this. And typically concentrations would be molarity. And if you happen to be doing something with pressures, standard unit of pressure typically is atmospheres. It's kind of the unit that you would want your pressures to be in. By the way, the value of K is actually just a number. There's typically no units associated with it. So K is really just a number. And we can think about what K tells us. So for example, if I have a large value of K, that means that when this reaction reaches equilibrium, I should mainly have products. And the reason for that is if you think K is basically products divided by reactants, only way to get a large number is you need more products than reactants, right? So large number on top, small number on the bottom gives you a larger value of K. Now, if you have a small value of K, the opposite is true. When this thing reaches equilibrium, you will mainly have reactants. And kind of the same idea, larger value of reactants on the bottom, smaller value on top will give us a smaller value of K. Now, there is definitely various degrees of that. There are some K values that are like times 10 to the 36 or something like that, really large values. And there are some K values that are like times 10 to the minus 54, which are super small values. And there's ones all the way in between in terms of equilibrium constant. So when we talk about something being sort of a large value of K or small value of K, we're talking about basically the big value of 1 is basically that. Anything above 1 is considered a large value of K. Anything less than 1 is considered a small value. So higher than 1 is a large value. And anything less than that would be a small value. Any questions on that there? All right, so as I mentioned before, K is always the same as long as the temperature stays the same. And temperature is really the only thing that can affect the actual value, again, in comparison between the two different temperatures. And again, the idea that you can start with all reactants, you can start with all products, you can start with reactants and products. It doesn't really matter as long as the temperature stays the same. We will come to rest at the same ratio of products to reactants and give us our same equilibrium constant. So here, if we were to write our equilibrium expression, we would take our products, which is the concentration of H plus, times the concentration of acetate in this case, divided by the concentration of acetic acid. So again, our products over reactants, all the coefficients here are 1, so we don't have to put any of those in there when we do that. They are all also aqueous, which means they're all good to go. This would be our Kc. There would not be a Kp in this case because there's no gases in this case. So you need gases to have any type of Kp happening. All right, so if we were to calculate the equilibrium constant here, once again, we could write our expression, which is our products, which would be our NO2. We would square it because of the coefficient. We would divide it by the concentration of N2O4, and they gave us equilibrium concentrations here. So as we can see on the bottom there, we would put it in the correct location. And our 0.055. I assume they have the right answer, but you never know. I feel like there's a mistake on one of these. 0.065 looks good. That would be considered a small value of K, which means when we reach equilibrium, we should actually have mainly reactants sort of happening in this case. Questions on that there? So again, needs to be equilibrium concentrations to go into that, and basically just plug it in. Again, no units associated with it. All right. So as I mentioned, homogeneous equilibrium, everybody's in the same phase. And again, in this case, we would include everything in each of these, and we could write our equilibrium expressions. And in the first case here, it would be the concentration of NH3 squared divided by our N2 and our H2 cubed. For our second one, it would be the concentration of H plus times the concentration of Cn minus divided by HCN in this particular case. Again, just our products over our reactants. Now, in heterogeneous equilibrium, we do have some other things involved. And as I mentioned, solid and liquid are not included in the equilibrium. So if we were to write our equilibrium expression for the first one, it would be the concentration of O2 cubed. This would not be included because it's a solid, neither would this. So that would actually be our equilibrium expression for this particular one. Now, when we look at the second one here, our equilibrium would be the concentration of H2 squared times O2. And once again, that is a liquid, so we would not include it. By the way, though, if you did have water that was a gas, you would include it because it is a gas in that case. So here, though, in the liquid form, we would not include it, which is probably your common one. Now, for some reason, you had a equilibrium where maybe this was solid and you had some aqueous stuff over there. What you would do is actually just go 1 over basically your products. And since there's nothing on the product side there, 1 over reactants. Since there's nothing on the product side there, you just do 1 over the reactants if you had something in that situation. Any questions on writing those there? All right, so again, there we go. And our equilibrium expression here, we would not include our reactants, so it'd be just our calcium times our F minus squared in this particular case. Again, because of this being a solid, would not be included. All right. All right, then let's talk about the last thing here, which is Le Chatelier's principle, which we did that experiment together the other week. Le Chatelier's principle, as we talked about, is the idea that you have this system at equilibrium. So you have this nice system that is at equilibrium. And again, it's going back and forth at the same rate. You basically do something to it to mess up the equilibrium. So you have this guy is at equilibrium. You add a stress to the system. It's going to mess up the equilibrium, but because this is a reversible reaction and an equilibrium reaction, it will want to reach equilibrium again. And it will cause the reaction to shift, as we talked about. And you can shift to the right, which means you would need to make more products. It may cause it to shift to the left, which means you need to make more reactants. And in some cases, as I think we even saw in some of those examples there, you could do something to it that might cause actually no change to occur. So when we talk about things that are stresses, and we focus a lot on in the lab about concentration, which is one thing that you can do, which basically you can either add or remove. That is something that could cause a stress to the system. If you're dealing with gases, pressure and volume is something that you could do. Temperature is also another one that you can do, and a catalyst. So these are several things that you can sort of do to a system that's at equilibrium that may cause it to have to shift one way or the other to basically get back to that equilibrium sort of position. So we're going to talk about all these guys here again, and we'll get into the ones we didn't really talk about the other day. And we'll start with concentration. So once again, in terms of concentration, the two things that you could do, as we talked about there, is you could add more. And when we add more, it will typically shift away from the side you added it to. And that means if you add reactants, it will go towards the products. If you add products, it will go towards the reactants. The other thing you could do is you could remove. And when you remove, it will actually shift towards the side you removed it from. So if you remove reactants, it will go towards it. If you remove products, it will go towards it. So the idea is sort of this deal. I don't recall if I drew stick figures or not, but we'll redraw them here. So if we have a system that is at equilibrium and we're all happy, and if somebody does hop on, say, onto this side, our product side here, we're going to get this situation that's going to occur. And now we're clearly out of equilibrium in this case. And now to fix this, we would need to put more people on the left-hand side or the right-hand side. You put more people on the left-hand side. So we would shift away from the side that we added it to, and we would need to put more people on there to get it back to sort of equilibrium. And at this point here, we would return to an equilibrium position once again. So when we add, it always goes away. So AA is a good way to remember that. Again, if you add reactants, it should shift to the product side. If you add products, it should shift to the reactant side. Now, if we have kind of the same situation here, and we have, again, a system at equilibrium, and this guy decides he's going to basically jump off. When he does so, this is going to be the result of that. And in this case, to fix it, we would have to shift towards the side, basically where he jumped off of, and that's going to return us back to equilibrium positioning by that. So again, it will go towards the side that is you removed it from, and again, it'll go away from the side you added it from. So how do we add more? Kind of like what we did in the experiment. You simply could just take the reagent off the shelf and dump it into your beaker, and you could add more, whatever it is. You could add something that's a source of whatever ion maybe that you're looking at in that solution. How we remove something is a little bit different. You can't just kind of reach into the solution and pull out ions. So very commonly, the way that we could remove something is when we have ions that are floating around in a solution, you could add something to that solution that may react with one of the ions that are floating around and make something that's a solid, for example, make a precipitate solid. Remember, solid is not part of the equilibrium, so that would be essentially like reaching in there and pulling out that ion from the solution, and that is one way that you could remove it. Another very common way that you could remove something that has, say, hydroxide or hydrogen ions floating around is to add either hydroxide or hydrogen ions to it. And when those guys get together, it will make water in that particular case. And although you can't necessarily see that you made water, it would be essentially, in my example there, a way to go in and take out the H plus ions from the solution, and that would remove it. Or if you want to remove the hydroxide, the OH minus, you could add some acid to it, and that would provide an H plus that will react with the OH minus and remove it. Water, which is a pure liquid, won't affect equilibrium either. So again, that is a way to sort of reach into a solution in a sense and pull out those ions. Any questions on that there? All right, so now in addition to concentration, when we talk about pressure and volume, they are oftentimes sort of tied together. And if you remember our friend Boyle, perhaps, right, there is a relationship between pressure and volume. As the pressure goes up, the volume goes down, right? And vice versa. As pressure goes down, the volume goes up. So these guys are related to each other. If we increase the pressure, that means that we decrease the volume. And the sort of change that's happening here is we kind of rose the pressure. So we brought the pressure up. So what we want to do is kind of bring the pressure back down. So in that situation, we have now a much smaller volume. And in that smaller volume, we would actually need less gas molecules. So it would shift to the side with the less number of gas molecules. And it will shift whichever way has the least number of gas molecules. That obviously is dependent on the equation that you're looking at as to which side has more or less gas molecules. It is as simple as finding everybody with G's on each side and just taking the coefficients and adding them together, and it'll tell you how many gas molecules you have. Opposite is true. If we kind of lower the pressure, that means that our volume has increased. So now we have this much larger volume. And the way to fill it is we need a lot more gas molecules. And the reason for that is basically we have lowered the pressure. So we kind of want to bring it back up. So the only way to bring it back up in this really big volume is we need more gas molecules, because more gas molecules means more collisions, and that should help bring the pressure sort of back up in that particular case. So we go to the side with more gas molecules. So for example, if we had this, and we did these things here, we added more C, we increased the pressure, we removed B, we added more A, we increased the volume. So for each of those, decide will it shift to the right, to the left, or no change. Take a moment for each of those and see what should happen in this case. Okay, so let's take a look. We'll start with adding more C. So C is a product. Remember that when we add it, we'll add away, right? AA. So since we added products, we should expect it to shift to the left there and make more reactants. Really, the reason why that's going to happen is in this case, we added more products, which means there's more products available to start reacting, which is going to cause the reverse reaction basically to occur. And that's why it's going to shift away from the side we added it to. Now, when we go to increase our pressure, that means that we do have a smaller volume. And I personally think about pressure and volume as the volume part of it, and small volume means less. So small less, so less gas molecules is what we need in this case because we have a much smaller volume. So in this case, we just add up everybody with G's, that's 3, and 2 is 5 gas molecules, right? On this side, we have 3 gas molecules. So it actually will shift to the right in this case because that has the least number of gas molecules. Any questions on that one there? If we remove B, it will always go towards the side you removed it from. So that should cause it to shift to the left in this case. Again, you can think of it as really 2 ways. One way, if it's easy to think about it, is you remove the left-hand side there, you kind of created a hole, and you gotta want to fill the hole. So it's going to go towards that hole and fill it. What's really happening here is kind of the same idea. You remove reactants, which means in this case, you now have more products available. And more products available is going to cause a reverse reaction to occur, and it's going to head towards the reactant side in this case because of that. Adding more A is over here, so that's a reactant. Again, that's going to cause more reactants to be available and going to cause the forward direction to happen, and it's going to shift it away. Lastly, here we're going to look at a larger volume. That means really our pressure is going to go down. So to bring our pressure back up in that bigger volume, larger volume, more gas molecules, which in this case would be shifting to the left. Any questions on any of those there? So the last couple of things that could affect Le Chatelier's principle deals with temperature. And let's talk about temperature. And temperature basically works the same as concentration, which means if you increase the temperature, it will shift away. Get that right. If you decrease the temperature, it will shift towards it. Now, you can increase the temperature very simply by just taking your test tubes or whatever you're reacting, just put them like in a hot water bath, and that would increase the temperature, obviously. You can also remove the temperature by throwing it on ice as well. So you can throw the test tubes on ice, and that'll be like removing it. So what really determines sort of what's going to happen is basically where you think about the temperature, heat, or energy is going to be. And that has to do with what type of reaction. Is it a exothermic reaction, which, as we know, heat is released, right? Our energy is released. And when we think about an exothermic reaction, we think of heat and energy as being a product. So we think of it as being a product. And usually, as we talked about, exothermic reactions are given with delta H's that are negative, right? So negative energy values are typically our exothermic type processes that's occurring. And that's different than if I had an endothermic reaction. That is where heat is absorbed. And when we think about endothermic reactions, heat and energy is considered a reactant. And our delta H would be positive in that case. Again, positive numbers is endothermic type processes. So it does depend on obviously what type of reaction you're dealing with. Once you identify that, you then know basically where heat and energy is. And if you increase the temperature, it goes away. And if you decrease, it will go towards. So in an exothermic reaction, if you increase the temperature, it would shift to the left. And if you remove the temperature or heat, it would go to the right, and vice versa there for your endothermic reaction. Lastly, in terms of what could affect the equilibrium is a catalyst, and a catalyst is actually, again, not a reactant as we talked about. It's not a product, and it does not get used up in the reaction. It is there really just to facilitate the reaction occurring faster. It actually will cause a no change situation. So that's one of the things that will cause a no change. If you added a noble gas, for example, noble gases are chemically inert. They won't react with other things. That also could cause a no change situation. And probably the third case where you could have like a no change situation, by the way, is in that sort of pressure volume when you're counting up gases. There could be a situation where you look at an equation, you have the same number of gas molecules on each side, and that's going to be a push. So there is going to be no side that's greater or equal. So in this previous one here, if you had equal number of gas molecules on each side, it would also cause a no change because there is no more or less gas molecules on either side. So there are a few places where a no change could kind of happen. So let's take a look at one more here. Let's just do and for the fun of it here, I'm not sure if it's right or not. It's just a made up number, so it's probably wrong, but we'll just make it this one for the sake of this example. It's definitely not the right number, but we'll just go with it. All right, so we're going to, in each of these cases, shift to the left, to the right, or no change. If we increase the pressure, remove NH3, we decrease the temperature, we add some N2, we increase the temperature. Let us add some H2. Let us increase the volume. Let us add a catalyst. All right, so for each of these, which way are we shifting? See what you come up with. See the pressure, that again means that my volume should come down. Again, smaller volume means I need less gas molecules. So in this particular case, we got 4 gas molecules there. We got 2 there. So it should shift in this case to the right towards the least number of gas molecules. Here we're going to remove NH3, which is a product. That's going to create like a hole on the product side, and we would need to kind of fill that hole. Also would mean really that we have more reactants than products, so the forward direction of this reaction is going to take place. Here we're going to lower the temperature. We want to look at a made up delta H value here. And really, the number is not that important. It's actually the sign. In this case, it's a negative delta H or a change in enthalpy. That means it is exothermic. And what that also means is then heat should be considered a product in this case. And because of that, we're going to lower it. It would be like removing a product, which again would cause a hole on the product side and would cause the reaction to shift towards it in this particular case. Any questions on that one there? Here we're going to add N2. N2 is a reactant. That's going to increase our reactance and cause the forward reaction to occur. And it will shift away from where we added it in this case and would go to the right. Here we're going to increase the temperature. So because this is an exothermic reaction, we already established it is going to be on the product side. That's going to cause more products and it's going to shift away and go towards the reactant side in this case. Adding our H2, adding more reactants will cause it to shift away and the forward reaction to occur. And increasing the volume means, by the way, my pressure is coming down. So to bring my pressure sort of back up in that larger volume, we would need more gas molecules. So that would shift it to the left in this case, which has more gas molecules. And lastly here, to add a catalyst, we'll actually have no change in this case. Again, it'll just get to equilibrium quicker. Any questions on Le Chatelier's principle? All right, well, that wraps up Chem 3 for the season, I suppose, yeah.